right, welcome everybody to Standing for Truth. My name is Donny, and I am your host for today's program. I am thrilled, as always, to have my brother Michael J. Oard here with me for another important show. Mike has been a huge blessing to the Standing for Truth ministries. He's been extremely generous with his time, and you can find all of his previous presentations on the Standing for Truth program linked in the description box of this video. You'll find presentations such as the receding floodwaters, the Ice Age, answering many challenges and refuting objections. You'll also find programs on the Green River Formation, the Grand Canyon, flood boundaries, and more. Now, today's program is specifically dedicated to ice cores and the age of the Earth. Mike's talk is titled, "Do Ice Cores Contradict the Bible?" Now, before I hand it over to Mike for his presentation, I do want to give our guest a formal introduction. Michael has a master's science degree in atmospheric science from the University of Washington and is now retired after working as a meteorologist with the U.S. National Weather Service for 30 years. He has researched and speaks on the compelling evidence for Noah's flood and the Ice Age that followed, and how the incredible woolly mammoth connects to biblical history. Michael has published many papers in his field in widely recognized journals and has written An Ice Age Caused by the Genesis Flood, Ancient Ice Ages or Gigantic Submarine Landslides, the Missoula Flood Controversy, which he's given a presentation here as well on, and the Genesis Flood and the Frozen Record. He is also author of Frozen in Time, The Weather Book, and Life in the Great Ice Age. And behind me, I've got a few of those books, as a matter of fact, Frozen in Time and Biblical Geology 101, which is, I would argue, a must-have book. And so with that, Mike, as always, it's great to have you. I do appreciate the time that you give us for these programs. I know how busy you are. And so, Mike, how you doing today?
Oh, I'm doing quite well. Thank you.
I hope your 2024 is going well so far.
Busy as usual. Yes.
Of course. Okay, brother. Well, I'm excited for this. I think we'll just get right into your presentation. I got your slides here up on the screen and ready to go. So, Mike, the floor is yours.
Okay. This is a topic that I've worked in for 20 or 25 years off and on. And so I've revisited it with new information. And this is part of a layman-friendly book on the topic that is being finished up with Creation Ministries International. So the title of my talk is, "Do Ice Cores Contradict the Bible?" And it's going to be a 5-part presentation. Here's the overview. There's no 110,000 annual layers in the GISP-2 Greenland ice core. There's no 800,000 years in Dome C Antarctic ice core. And then I'm going to explain the ice sheets within biblical Earth history. And then I'm going to change from large-scale ice core to finer details, which they consider the millennial scale, and they have an explanation for these radical or catastrophic millennial changes they claim, and an explanation for the Green Sahara. So let's do the first talk. But before we get to that, a few, I have a little previous. Okay, we must remember some things, that this issue is not about observations of science that are contrary to the Bible. There are no observations of science contrary to the Bible. It's interpretations based on naturalism that are contrary to the Bible. And there's several naturalistic assumptions. Uniformitarianism in deep time since the late 1700s. It was informal in the late 1700s, and it became formalized with Charles Lyell between 1830 and 1833 with his Principles of Geology. At the time they assumed uniformitarianism in deep time is your millions of years, there's little known of science at the time for them to make those assumptions. For instance, they did not know the origin of basalt and granite. And ever since the late 1700s, naturalistic assumptions are locked in concrete ever since. They're dogmas that they can hardly challenge. And as a result, the Bible, especially its short time scale, is totally rejected. The flood's rejected, the creation's rejected. But people should realize that the Bible has withstood the test of time from an army of critics. They say all kinds of errors, claim all kinds of errors in the Bible. For instance, one just called to my attention was that Pilate was a figment of the imagination of the New Testament writers. But now, thanks to archaeology, we've dug up features that name him. So, I mean, this happens over and over again. So, as a skeptic that are listening to this, you should take notice that the Bible has withstood the test of time. And it might be possible because of that its origins are solid. Anyway, let's get back to the ice sheets. We have two major ice sheets we're going to be talking about. The Antarctic ice sheet. It started forming 40 million years ago, they say, and reached equilibrium about 15 million years ago. They used to date it as maybe about 3 million years old, but because of what they think are features in the bottom of the ocean, ice rafted debris that they claim are about 40 million years old. They claim that it's had to start then. So it pushed back the age of Antarctica about 40 million of 10 times. The Greenland ice sheet, you can get all kinds of ages for that. In general, it's just supposed to only be several million, 7 million years old, and has been in equilibrium since. But there is papers you can get that say by ice rafted debris that maybe it's as old as the Antarctic ice sheet. So anyway, that's when the ice sheet supposedly started within the naturalistic worldview. And here are two ice core challenges I'm going to talk about before I get to explaining them from the biblical worldview. The GISP-2 Greenland ice core is said to be able to detect 110,000 annual layers, just like counting the rings in a tree to determine the age. Okay, well, that sounds pretty challenging. It is. And one ice core in East Antarctica, Dome C, is believed to have reached 800,000 years, showing 8 interglacial cycles that oscillate every 100,000 years. Anyway, we'll be getting into that more. So as a result, ice cores are considered huge challenges to creation science. Here's one by Bill Nye, the science guy. He's quoted as saying, let's say we have 680,000 layers of snow ice in 4,000 years since the Great Flood. That would mean we would need 170 winter-summer cycles every year for the last 4,000 years. I mean, wouldn't someone have noticed that? Wow. Wouldn't someone have noticed that there's been winter, summer 170 times in 1 year? Well, Unfortunately for Bill Nye, he probably should have read a little more about ice cores. First of all, he kind of assumes we're pretty stupid. Anyway, there are no 680,000 layers, annual layers, in either the Greenland or the Antarctic ice sheet. The Greenland ice sheets claimed only to 110,000 annual layers. And the ice accumulation on East Antarctica is so slow, maybe about 5 centimeters a year on the average, that it's too thin to produce annual layers. So it's dated by a totally different method. So he got it wrong. But Hugh Ross on his website challenges this way. Studies of ice cores affirm the antiquity of Earth and pose a serious challenge to young Earth models. Layers in ice cores, that's cylinders of ice removed from an ice sheet, can be used to determine ages if the layers are deposited annually. Assuming annual layering, high-resolution ice cores from Greenland and Antarctica give ages in the hundreds of thousands of years, indicating Earth is at least that old. Again, he thinks there's hundreds of thousands of annual layers, which there are not. He continues, recent work conclusively demonstrates that events occurring on century and millennial timescales in both cores correlate with each other. Actually, they don't correlate. More on that later. Furthermore, the cores show variability matching periodicities in Earth's orbit that occur on millennial timescales. These results corroborate and strengthen reason to believe RTB's old Earth model present an awkward fit if they can fit it at all in young Earth models. Again, Hugh Ross gets some stuff wrong here too. First of all, Earth's orbital geometry, that's the Milankovitch mechanism or the astronomical theory, does not show millennial or centennial scales. It has cycles of 23,000 years approximately, 40,000 tilt cycle, 100,000 eccentricity cycle. So it doesn't relate to that at all, even though that's a major assumption that goes into these. So this goes to show you that you need to get our position down correctly before you challenge it. And like I do, I try to read and find out what the secular scientist, the conventional model, says before I say any more. So this is my theme verse when I hear challenges like that. Examine everything carefully. Hold fast to that which is good. I'm holding fast to God's word. God's word has proven true over thousands of years. And holding true to the Bible, I'm going to examine everything carefully. Now, I'm emphasizing carefully there because if we analyze things at a superficial level, which is what Bill Nye and Hugh Ross did, you're bound to get into trouble, which they did. But you got to dig deep. And when you dig deep, you find a different solution, which is what I have done with the ice core challenges. So let's get into some basic glaciology. Here's a typical ice sheet. Ice accumulates at the top and it presses down the layers, and the layers flow out into the ocean and they become vertically compressed with time until you get towards the bottom down here. The annual layers, the blue layers are annual layers. The annual layers are, according to this model, as thin as a dime. That's assuming that the ice sheets have been in equilibrium, generally this high, for millions of years. And so you get one layer of ice, and further layers, annual layers, are pressed down on it, and it thins out vertically and squeezes to the side. So that's usually what happens in these annual layers. And in the annual layers, you have diffusion, which tends to homogenize the record. You have vapor diffusion, which is through the air pockets, and then you have diffusion between the ice crystal and the vapor. Two kinds. Actually, diffusion within the ice, but it's so slow that it doesn't really count for much. But this is in the top layers called the firn snow. You have a lot of layers. So as every layer presses down, the air in there gets squeezed out with time, and by about 100 meters at the most, all the air is squeezed out. Well, mostly so. What's remaining are bubbles in the ice, and it's those bubbles that they measure the carbon dioxide and methane and other gases that enter into the ice core research. But diffusion mixes the signals, and layer thinning thins them. So you do get nice annual layers at the top of the Greenland ice sheet, but as you get down deeper, diffusion and layer thinning makes it difficult to determine an annual layer. So you're kind of getting a hint at what's going to happen. Anyway, let's take a look at the Greenland ice sheet. And these are the ice cores. Milcent and Crete are very shallow ice cores. GISP 2, which is the one drilled by the United States, and GRIP, drilled by the European, are at the very top in the early 1990s. Since then, they got North Grip to the north, NEM, and East Grip is the latest one. Camp Century is the first ice core ever drilled, and then Die 3 at the very southern part was drilled quite a long time ago. So that's the ice sheet. It's about 3,000 meters thick in the center. And here is some profiles with what's called oxygen isotope ratios, which are generally proportional to the temperature. And this is the Camp Century core, the first core drilled in the middle 1960s. And you can see as you get to more negative oxygen isotope ratios, it's generally or roughly proportional to temperature. So the temperature cools to the left. So as you see this, the bottom part of that core is the ice age part of the core. And then above the ice age is post-ice age ice piled on. And then below, you'll see a warm part. That's the early part of the ice age when it's building. So it only shows one ice age. And it very much goes along with what we've been saying about only one ice age that followed the flood. Here is the Die 3 core. That they didn't smooth this too well, but it's generally about the same. There aren't a lot of big changes above the ice age. The ice age is the part that's to the left, so it's a very thin ice age. It probably was a lot thicker. Compression is pushed these layers down, so the ice age part is only several hundred meters thick. And here's the GISP 2 core, which I'll be talking a lot more about. It has a thicker ice age in it. It's about 1,500 meters above the deep, down to about 2,800 meters is the ice age portion. Above that is the post-ice age. Notice all those radical wiggles in there. Those are your millennial time changes. I'll be talking more about those, but in general, I'm going to talk about the main profile. I want to point out that before you get to the post-flood ice age, you you're starting to warm up, and then suddenly a cooling called the Younger Dryas, and they claim it lasted maybe about 1,400 years, and then it warmed back up to modern temperatures. Here's another plot of it. The Pleistocene, or the Ice Age time, you had the Bowling Ailerod rod event, which is the warming, trying to get out of the Ice Age at the top, and then suddenly a cool plunge to the Younger Dryas, and then it warms up again into what's called the Holocene, which is the last 11,700 years. So back to this diagram. No, I'm going to skip that. Oh, yeah. It depends on how old the ice age is as far as the annual layer thickness. The uniformitarian model, like the present slide showed, previous slide, I would say, you have nice annual layers at the top, about 0.2 of a meter, or about 25 centimeters of ice every year. Shows nice annual layers, but the annual layers thin way down to where it gets to be as thin as a dime. But we have a different view, which I will talk about later. Our model would indicate during the Ice Age part, which is this part right in the top half here for GISP2, we would assume that accumulation of ice was in meters per year. And the reason this tails off like this is because of compression. The deepest layers are compressed the most. So, and these are compressed some. So this is probably about 6 meters a year, compressed down to 3 meters and 2 meters at the very beginning. That's our general model that we would predict. And I'll get into that as we go. So when they first drilled the GISP2, they have all these ice age interglacials and events. And they thought that they found them in this GISP2. So you could see the time scale. You could see the time really increases down here. This little thing in here is 50,000 years. So they have all their events that they thought were there. But that is no longer true anymore, because it's found out that the bottom part, which would include most of this down in here, is deformed. The bottom of these ice cores are deformed, probably because of motion. And so you cannot do this. So that's been totally erased. And here is the Camp Century core again. And what you saw there, this is the Camp Century core plotted by time. As you can see, because of the thinner layers, most of the top part of the core is just up in here, but then all your time is down in here, down to about 120,000 years, they claim. So you can see what they've done by stretching out the bottom, by assuming it's been millions of years old. So let's talk about the seasonal cycles that they use to count annual layers. There are 3 main variables used in counting annual layers down the GISP2 ice core. They are oxygen isotope ratios, or oscillations, differences in acidity, and cloudy clear bands called visible stratigraphy. Here is an oxygen isotope record in the Milcent ice core, showing you how the nice annual layers show up. And these are fairly recent. You see 1950, 1960, 1970. Nice annual layers show up from the oxygen isotope ratio, which is generally proportional to temperature. So down on the bottom, you have the temperature scale. These are black areas are interglacial. These are the summer layers, and these are the winter layers. So everything is nice and neat at the top. And here is a diagram of an annual cycle and in oxygen isotope ratios. In summer, it's more positive. In winter, it's more negative. But there are many variables that are annual layers that you can use. And I only put the ones on here that apply to the ice cores that I've been using. For instance, in the winter, you get a lot of dust because the winds are stronger. And in the dust, you have a lot of sea salt spray. That's where you get your sodium, Na, and dust from continents, calcium. But in the summertime, you get these depth hoar complexes, which are like frost. And there's a series of them. There's not just one. So you got a depth hoar complex. And that's when your sulfuric acid is mostly deposited on the ice sheet. So the depth hoar complex and the dust are your clear cloudy bands. And the oscillations in oxygen isotope, that's one layer there. And then you have these acidity layers. So how do they do as they go down the ice core? Well, the oxygen isotope ratio quit at 300 meters deep. That is really strange. I haven't read why, but probably because you get down there, just too much diffusion and annual layer thinning. The acidity layers are mainly in the post-ice age time. They don't do you much good in the ice age part because the ice age had much more dust, and that dust reacts with acid and neutralizes it. So they can't use it. And that leaves only cloudy, clear bands in ice age time, which is 90% of the time. So 90% of the counting is these cloudy, clear bands. So let's take a look at some of them. Oh, I will summarize the cloudy, clear bands a little more. Depth hoar layers. They can be subannual, several of them in a summer, but difficult to detect more than halfway down the core, like the acidity layers you can't detect very far. Dust layers becomes the main method, especially deeper in the core, but dust layers can also be subannual. You can get more than one dust layer a year. And so here are segments of this, I think, is E-grip core. And it shows numerous cloudy clear bands. And you can see this is over about 160, 1.6 meters, each one of these. So you get so many of them, it's difficult to tell what is an annual layer and what is a storm layer, or even layers within storms you can get, as I will talk about. So it becomes very difficult to count as you get deeper down in the ice. And I'm going to give you some quotes. Looks like this one messed up a bit. A bunch of them to show the point. This is from Alley et al. 1997 Journal of Geophysical Research. In common with all other methods of layer counting, visible stratigraphy has certain weaknesses. Probably the biggest weakness is that the signal is variable along the full core length, sometimes subtle. Yeah, it's variable. That's the problem. I don't know why this is extending down so low. It didn't when I set it up. But anyway, here's another quote from Mies et al. Deborah Mies was the one who actually counted the layers and published them. in the Journal of Geophysical Research. Actually, she only published the results. She says, however, an increased particulate concentration, that's in your dust, may not be restricted to the spring or summer, and additional influxes of dust may occur during any part of the year, creating additional peaks of a non-annual nature. She admits that there's a lot of non-annual layers in there. Another quote, Swenson et al. Says, but because some years may experience more depositional events than others, some annual layers will appear as multiple visible layers. Multiple years appear frequently. So you got a problem of what you're counting down there. But I will get into that. But we got to really nail this down. Here's another quote from 2012, Climates of the Past. More often than not, however, the annual signal in the data is ambiguous. And when considered in isolation, these are not easy to use for layer counting. The idea is at such high resolution that it may resolve individual precipitation events. In other words, individual precipitation events are storm layers, and you get a lot of storms in a year. And this is from 2023. Cloudy bands are the main visible feature in the glacial ice from deep polar ice cores. They are important but poorly understood factors regarding climate reconstruction and internal deformation. Got cut off, unfortunately. And he continues, our visual and chemical investigations show that cloudy bands are more complex and diverse than previously thought. Cloudy bands are commonly interpreted as storm events. Listen to that. In spring and summer, transporting large amounts of dust from Asian deserts across the Greenland ice sheet. Here's another quote that indicates that storms, they have a variability. They have a warm sector and a cool sector. And in the process, they can have a cycle that is greater even than the annual cycle. Now, delta D up there is similar to oxygen isotope ratio. This is the deuterium isotope ratio. It works the same way as oxygen isotope. But anyway, he's admitting that we observe changes up to 90 per mil in delta D content of the precipitation samples at Niem, that's in northern Greenland, during the passage of a cyclonic storm. One storm. This is relatively large compared to the annual amplitude of only 50 in delta D. So these storms produce huge differences in these variables. But they assume that diffusion and layer thinning wipes them out. But it doesn't. It depends on how your accumulation rate. If you have a thin accumulation rate, yeah, but if you have thick accumulation, it doesn't wipe out anything. That's what I'll get into. And there are even, within storms, you get oscillations. This is a drift from a blizzard around Minnesota a couple years ago. I thank Peter Anthony for this photo. This is one drift, and you can see there's dirt bands in it. And so within one storm, you can get variable dust layers. And I had to throw up a daily weather map here. This was the blizzard close to Christmas time, 2022, that produced that 1 meter high drift. Actually, there were some drifts 2 meters high. So there's actually 4 secular ways to date ice cores. Annual layer is just one of them. Because of all the confusion as you get deeper in the ice, you got to use another method. And what you do is glacial flow modeling with reference horizons or tie points. In other words, they have a flow model. The flow model assumes the age, millions of years, and they tie it to various events within their ice age paradigm. And that anchors the flow model. the flow model is the first guess before you start counting annual layers. And you count annual layers and you can't deviate too much from this first guess. But all this flow model and the reference horizons or tie points are compared to the Milankovitch insolation changes. In other words, the Milankovitch insolation or sunshine changes drives the dating of these ice cores. In fact, it drives practically every climatic data set. They assume the Milankovitch mechanism. So here's the flow models. Depending on how the accumulation you get, if it's over millions of years, you end up with very thin annual layers at the bottom. But if it's rapid accumulation, the annual layers are very thick at the bottom, and this would not apply. So their flow model, based on their assumptions, sets in concrete what you would expect for annual layer thinning. And I have several quotes to back that up, but I found this latest one here, or this one right here. It's actually rather old, but it says it all. Preliminary modeling for the age distribution should be carried out before the drilling and the core analysis. In other words, you do the flow modeling and with the tie points, assuming the Milankovitch mechanism first, to give an initial indication of the age-depth relationship, which can later be improved with the addition of ice core data. In other words, they assume it's old, they set up a system, and they get old age out of it. It's circular reasoning. This property, the strain rate, 3 times higher during the last glaciation than the Holocene, has important implications for ice sheet modeling, the most frequently used method for dating ice cores. See, dated by flow modeling and tie points. Yeah, tie points a lot of times are not published, but in an Antarctic ice core called RICE, that's the latest ice core they have down in Antarctica. They actually published them in 2 articles, all their tie points. And these tie points are already dated by their dating methods, and old age is built into it. I don't know if you can read any of that, but mostly volcanic eruptions are tie points, but most of them are unknown. One of the best ones on here is Krakatoa right there where my cursor is. And go to some more. Taupo, New Zealand. That day is dated 236 AD. But that's the last tie point they have for this rice core. The other ones here are unknown. Until you get into some ice age events. The Younger Dryas is right here, and other terminations, so forth. Now, the Great Toba eruption, about 70 to 75,000 years in their time scale, is considered the strongest eruption that we know of. And it's been used as a tie point for various things. But guess what? It's not even here for this. So anyway, that's it for the rice ice core. So in summary, flow models and tie points, they're the intermediate dating method. And they assume ice sheets in equilibrium for millions of years. And the tie points are from other data sets that anchor the flow model. And the model has old age automatically built in. And it provides a first guess on the expected annual layer thickness. So they're not actually counting annual layers. They're assuming certain things, mainly old age. and producing annual layers to back that up. Now, some of the ages of the reference horizons are determined from deep sea cores, from other climate records such as speleothems, pollen cores, lake cores, Loess Paleosol sequences, etc. But all these records are dated by Milankovitch mechanism, the fourth and main dating method. So they don't. This is that's very come out with thin layers because of their flow modeling and tie points and the Milankovitch mechanism. Now, the 110,000 years is really based on circular reasoning, even more so than I've already told you. When GISP 2 was first dated, it was dated to 85,000 years at 2,900 meters near the bottom by Misa et al., published in 1993 and 1994. But it did not agree with the Milankovitch mechanism. It was too young. So they were told to go back and recount. So Misa et al. Increased the resolution of this instrument that detects cloudy bands, laser light scattering, I think that's what that stands for. They increased the resolution from 8 millimeters to 1 millimeter. And guess what? They picked up more wiggles. They found 25,000 more annual layers in the bottom 500 meters. 25,000 more. So GISP 2 ended up being dated 110,000 years at 2,800 meters. This is straight in the literature. Misa et al. 1997 from the Journal Geophysical Research. They had a whole issue dedicated to ice cores, and it's in that. So it's plain as day that it's circular reasoning to the Milankovitch or astronomical theory of the ice ages that claims that ice ages oscillate every 100,000 years. So here's kind of my perception of how they must have done this. This instrument, LLS resolution, gave, we'll say, suppose 10 annual layers. You can see there. But when they increased the resolution by 1 millimeter, they got more wiggles. And so the supposed annual layers, you can see on the right there, anyone want to count them? Many more. So I think that's how they did this. Picked up a lot more wiggles than 500 meters at the bottom. And they, in diffusion and layer thinning, storms, this is 1 year here. On the left there are the wiggles you expect in all the variables within one layer. And so you can see that there's an annual layer in there. And they assume that these diffuse out by their and be a nice curve of summer and winter. But if you had a lot thicker accumulation, like in the biblical model, they would stay there. They wouldn't diffuse out because an annual layer may be 6 meters. And you can compress it some, and there'll be some diffusion, but you're going to keep those those oscillations within an annual layer. And so they're going to count every single one of those as an annual layer in their method because of their assumptions that the ice sheet is old, been in equilibrium for millions of years. So it's old age in, old age out. It's really as simple as that. So there's no 110,000 annual layers in the GISP 2 Greenland ice core. But what about the Donny Sea ice core, where they claim there's 800,000 years? Well, we'll get into that. But let's take a look at East Antarctica. These plots are recent. Here's the Rice core right here. It's on a dome within the Ross Ice Shelf. And here's the thicker East Antarctic ice sheet. It's up to 4,000 meters high at Dome A. But the West Antarctic ice sheet is a lot thinner. And the ice, some of the ice cores I'm going to showcase. Here's Dome C. That's the main showcase. Here's Vostok, drilled by the Russians. Here's Dome F, drilled by the Chinese. Dome A is actually, drilled by the Japanese. Dome A by the Chinese. And this is a recent one, Conan Station right there. But anyway, it's a lot thicker. The ice is anywhere from 3,000 to 4,000 plus meters. In the bedrock, there are some deep rifts. So it's a lot thinner in those, thicker in those rifts. So the West Antarctic ice core, ice sheet, has two main deep ice cores. Bird core, that was the second ice core drilled in, I think, 1968. And a more recent one is called Waist Divide, which stands for West Antarctic Ice Sheet Divide. That's on the divide here. And as it turns out, this bird core, if you raise the land, because of the ice presses the land down, but if you raise it back to the beginning, this bird core would have been drilled in ice accumulated at sea level. But this Waist Divide one is about 1,000 meters below sea level, because West Antarctic is a series of mountains and with ocean between. I will show you a picture later on. And the Transantarctic Mountains separate the West Antarctic ice sheet from the East Antarctic ice sheet. So here's the bird core. And they have two variables up there at the top, oxygen isotope ratios and deuterium isotope. They're generally plot the same. There's a difference of about 8 times. So anyway, you go down and you see their time scale to the bedrock. They only got to 75,000 years. And in their time scale, that's only 3/4 of an ice age. Now, the Waist Divide ice core never even made it that far. It only picked up about half an ice age. So the West Antarctica ice cores are quite different than the East Antarctic ice cores that claim to pick up many ice ages. So here are some. This is Dome Fuji, and the way this works is the temperatures are colder to the left, the more negative oxygen isotope ratio. Each one of these wiggles going to the right is an interglacial. This is the current interglacial right here called the Holocene. This is the previous one right here. And then there's another one they claim right here that has 3 peaks, and another one down here at the bottom. So they have 4 interglacials. In between is the ice age. You can see the last ice age occurs over a little more than half this ice core. The bottom here, which they believe is greatly compressed, are 3 more ice ages. Another ice core drill is Vostok, but it happened to be drilled above a huge, deep lake. There are hundreds of lakes on the bottom of the Antarctic ice sheet, by the way. So it's cored above Lake Vostok. So it ended up having only 4 cycles too. Dome C had 8, which I'll get into. And this is the Vostok core. It's sort of like close to that Dome Fuji. By the way, that was an old plot of Dome Fuji. They have since added, I think, 2 more wiggles on the bottom. But you can see it's very similar to Dome Fuji. They're all East Antarctic plots in meters are very similar to each other. They have all these wiggles in here. This is the ice age right in here. So half down you get to the previous interglacial, they claim. So half the ice is due to the last ice age, and down below you got to count wiggles that go over to the right for your separate ice ages. And so you end up with 1, 2, 3, 4 other interglacials as you go down. But when you look at Dome C, that's called Epica Dome C, by the way, compared to Vostok, Dome C has more wiggles. Now, the bottom plot is a depth plot versus deuterium isotope on the left there. And it's very similar, but it only has 4 ice ages, but they're counting more wiggles in here. And I'm not very impressed with the wiggles, the amplitude of the wiggles past their 4th one here, like these here. They count these as ice ages. So that's how they get their 8. I kind of think it's Bush League. But anyway, it's very similar to half of the ice is from the last ice age. And then you got all these wiggles in the bottom half. And Vostok only has 3 more major ones, but they claim that Dome C, which is here, has 7 more, which the bottom 3 to me are really low amplitude. And here they stretch them out to 800,000 years. The green is Vostok, and here's the Dome C. And from 400,000 years in their time scale, clear to 800,000, you got these little tiny wiggles, and they count those as ice ages. I think there's a problem right off the bat, but we will let them have it to move on. So there's 8 of them there. So how are Antarctic ice cores dated? You cannot date by annual layers, despite what Hugh Ross and Bill Nye said. You cannot date by any radiometric methods, even though it might be possible to do it. Maybe the technology will allow it now. So the Antarctic cores are simply dated by wiggle matching those wiggles to deep sea cores that also wiggle, assuming the astronomical theory of the high ice ages. So they assume the astronomical theories, they get oscillations of 100,000 years, and they date deep sea cores that way, which they use to date the ice cores. That's a vast circular reasoning network, depending on how well the Milankovitch mechanism works. Now, the Milankovitch mechanism, it was rejected. It's an old mechanism, started in the middle 1800s, soon after the Ice Age was discovered. James Kroll was the first guy to work on it. And another guy named Adamar worked on it. And then Milutin Milankovitch was the last one who worked on it in the 1930s. Anyway, it showed cycles based on the orbital distribution of the Earth. Say the tilt cycle. The tilt cycle varies by 3 degrees, 21.5 to 24.5. And cycles every 41,000 years. Eccentricity cycle, which has no power at all, by the way. That's considered their main cycle, the eccentricity cycle of 100,000 years. Anyway, meteorologists have always said the mechanism's too weak to cause ice ages. And I have delved into this a lot. I have quite a few papers and books I've published problems with this. Now, you have to dig deep in this Milankovitch mechanism to see the problem, because a lot of times they're kind of sneaky on the way they present the radiation curves. They usually use one date, mainly the summer solstice, like June 21st, or the month of June. And yeah, you get a pretty good oscillation, but you can't just use it, and it's at 65 degrees north. You can't do that, but it looks good. But you got to use the whole hemisphere and the warm half year. And when you do that, the Milankovitch mechanism decreases to maybe 1% to 2% difference. But it was revived in the 1960s and 1970s from deep sea cores, supposedly proved. But they had to date these deep sea cores. And they changed the dating of one tie point. And Jake Hebert found this and reran all the data with that new tie point. And guess what? The oscillations that they supposedly got were off. Big problem. So ice ages supposedly oscillate every 100,000 years for the past million years. So here is a plot of ice ages. They believe there's about 50 ice ages now in the Pleistocene, which starts about 2.6 million years in here. And you can see all these big wiggles in here. They oscillate every 100,000 years, but about a million years, they oscillate every 41,000 years. You might ask, well, why don't they oscillate at 20,000 or 5,000 or 75,000? Well, because they're dating with the Milankovitch mechanism, which says you only have 3 main cycles, 2 of which are the 100,000-year eccentricity cycle and the 41,000-year tilt cycle. So there's a lot of circular reasoning that goes into all of this stuff. So they have 50 ice ages in regular succession now. And they don't get this on land because they find in most places just evidence of one ice age. And there's a good reason for that, because usually each ice age will destroy the previous evidence. They claim you can find it in deep sea cores where they wiggle down the core, these variables wiggle. And there's several variables. One of them is oxygen isotope ratios. When it wiggles over here, it's a glacial wiggle. Over here, it's an interglacial, and so forth. And you have dozens of these wiggles. And so that's where you get the 50 ice ages. And to show you that they use the Milankovitch mechanism, I have several quotes, but I'm not using those. I'm only going to use this one. The initial orbital dating in ice cores was inspired by orbital dating of marine cores, Embry and Embry. 1980 is a key reference. Assuming that the Milankovitch, that's another name for Milankovitch theory, linking ice volume and a high latitude insulation is correct. So there aren't any 800,000 years in the dome sea core. It's all assuming the Milankovitch mechanism, where they oscillate every 100,000 years for the past million years. And so everything's dated by assuming Milankovitch. Okay. Their ideas don't hold water, but can we explain these ice sheets? Well, we got to do some analysis on the ice sheets to do this. In our ice age model, we have the flood and then you have a rapid buildup of the ice. The time since the flood is on the bottom. 500 years is glacial maximum. 700 years, it all melts by then. And this is in the northern hemisphere, by the way. Southern hemisphere is different because The ocean water and the atmosphere are generally independent of each other. Same with volcanism. So that's our general model. And our annual layers are in meters per year, many meters per year. And we have 4 key assumptions, especially 3, to consider in interpreting ice core observations within biblical Earth history. Number 1, during the early ice age, we had warm water at mid and high latitude, causing much more evaporation. You can evaporate 7 times as much water vapor into the atmosphere at a sea surface temperature of, or air temperature of 86 degrees Fahrenheit than you can at 32 degrees Fahrenheit, 7 times. Number 2, as a result, there's going to be more rapid accumulation of snow and ice just because of the warm water evaporating more moisture. Also, we got to realize that because Greenland, the center of Greenland is low altitude, and because of the warm water, it's going to delay glaciation in the lowlands. It'll start it right away in the mountains. But Antarctica won't be like that, especially East Antarctica, which is mostly land right after the flood, and it would start accumulating snow right away. Also, we have to realize that the ice sheets have pushed down the land. So we got to raise it up for the start. It amounts to maybe 500 to 800 meters at the most. You have to raise the land. So anyway, here's the current altitude of bedrock in Greenland, where you have the mountains are the blue, the brownish colors, the green are low, and the blue is below sea level. You can see that the center of Greenland, where those ice cores are mostly drilled, right now is below sea level a little bit. But if you add maybe 800 meters of uplift for the beginning, that center part would not be below sea level, but it'd be low altitude. Because of the low altitude surrounded by warm water, it'd be slow to glaciate. See, it's called isostatic subsidence when the ice pushes the land down, and when you take the ice off, it pushes it up. Called isostatic rebound. So we got to take that into consideration. So, how many ice ages do these ice sheets indicate? Greenland shows only 1 ice age. West Antarctica shows only a partial ice age, and it's East Antarctica that shows up to 8 ice ages. So we need to deal with East Antarctica. Timing of the beginning is important. The lowlands of Greenland did not begin glaciation for approximately 150 to 200 years because of their low altitude and surrounded by warm water, warm onshore flow. And you know something? They've recently discovered plants and pollen and trees below the ice cores in Greenland, indicating that before the ice collected, they had a period of warmth that they grew some trees and some vegetation. But East Antarctica would glaciate right away because of its fairly high altitude to start with. So you got a gap in there, the timing, and that makes a big difference on how we explain these, as we'll show. Here's a diagram, a series of diagrams of postulated ice age occurrence. This is my first guess, you might say, educated guess. Anyway, you can see there's mountain glaciation, and then there's large areas that started. This is within 50 years after the flood. You'll notice Greenland. The western mountains are glaciated by 50 years, start to glaciate, and the western mountains are not. But after 100 years, both mountains are starting to glaciate. And after 100 years, 100 more years, up to 200 years, all of Greenland is glaciated except near the coast. So that the lowlands of Greenland didn't glaciate for 150 to 200 years. And that would be the plot of the accumulation, assuming no compression. You can see at the bottom, it doesn't start right after the flood. It starts about 150 years, and then it grows rapidly, about 6 meters a year before compression. But if you include compression, it was probably about 8 to 10 meters a year. Is that even possible? Well, I'll get to that. Here's Antarctica. Bedrock now, but you got to raise this bedrock about anywhere from 800 to 1,000 meters. So much of East Antarctica is going to be above sea level. It's got some deep rifts in here too. And here's the Gamzertsev Mountains where they believe ice occurred. And they send radar beams down and they can pick up features of these mountains, which I will mention as we go. West Antarctica, these are the Transantarctic Mountains here. So you can see West Antarctica is a series of mountains. But if you raise the land up, there's going to be more land to start the ice in these areas with the ocean in between. And this is 50 years. This is a plot of 50 years. Starts glaciating in the mountains of West Antarctica over here. Here's the east. Here's the Transantarctic Mountains. And then most of Antarctica is glaciated right away within 50 years. And then in 100 years, it could be like that. This is postulated now. This is my first guess based on meteorological reasoning. And then this is 200 years. And 300 years fills in the oceans. And here's East Antarctica and West Antarctica. So to correlate these ice sheets in order to figure out the ice accumulation rate on East Antarctica, you had to correlate them. And the only reasonable way to do this is by methane. Methane is a gas that actually within 1 year becomes generally homogeneous between the hemispheres. So you get methane oscillations in the air bubbles, and that can be used to correlate the Greenland with the Antarctic ice sheet. And when you do that, you find that the top half of East Antarctic ice sheet correlates to the total length of the Greenland ice cores. In other words, as Greenland started accumulating after 150 to 200 years, the top half of East Antarctica was accumulating, which implies that the bottom half of the East Antarctic ice sheet was deposited in about 150 years before compression. So let's take a look at this previous slide. Let's look just at the red Epica Dome C with depth. What it's saying is that the oscillations in methane indicate that this part of the ice, the top half, from about right in here on, correlates with all the Greenland ice sheets. So it's this bottom half that occurred before Greenland started, you see. So you got to accumulate ice to almost, currently it's about 1,500 meters of ice in 150 years. That's an average of about 10 meters a year. But if you do compression, it's probably 15 meters a year. So here's kind of a little diagram showing compression. So ice accumulates on East Antarctica in 150 years up to 2,250 meters. And with time, as you pile up more ice, as Greenland is accumulating, you push these layers down, with the bottom layers being pushed down more than the middle layers. And so it's pushed down to 1,500 meters now. But you have to collect about 2,200 meters of ice in 150 years. Is that possible? Well, we will check it out. Here's the accumulation rate. In order to get an average of 15 meters a year, and it's compressed more at the bottom, it probably has to start out at 20 meters a year, and after 150 years, drop to 10 meters a year. And then for the rest of the ice age, it collects more and more and slows down to maybe about 1,000 years is when you probably reach glacial maximum in Antarctica, because you had a larger ocean with more heat. It's the cooling of the ocean that times the ice sheet. And with a larger southern ocean, the glacial maximum in Antarctica would be later than in the northern hemisphere. And this is a key point to cause the Green Sahara, which I will talk about a little soon. So, is the East Antarctic accumulation possible? Well, in order to show that it is indeed possible, I will first examine high snowfall areas today, then understand the differences between today and the Ice Age climate, mainly the warm water, and then extrapolate to East Antarctica. So, this is a pass in northwest Japan. Northwest Japan and the Cascade Mountains of Washington and Oregon are the two largest areas of snow accumulation in the world. So this is what it looks like after a season. And by the way, not all that is water equivalent. You got to compress that down quite a bit. So you probably only have about 2 to 3 meters of pure water in there. But we'll go to Cascade Mountains, Mount Rainier, Paradise Ranger Station, about 1,700 meters above sea level. These are their stats. The snowfall from October to March is like this. And they get 14.2 meters of snowfall on the average. By the way, they have the record amount of snowfall in any 1 year period of 31 meters, by the way. So the average is much less than their world record. And here's the water equivalent. If you melt all that snow down to water, and this is by month, you can see that November, December, and January are about 0.45 meters a month. And Mount Rainier gets a snowfall by occasional storms that come inland, but they don't pick up a lot of moisture out of the ocean because the ocean is only about 10 degrees centigrade, and the air is. They get most of the precip because of orographic uplift pushing the air mass up the west side of the Cascade Mountains, which, if you know anything about the Cascade Mountains, by the way, I'm originally from Seattle, and my wife's from the other side of the Cascades in Yakima. The west side of the Cascades is a rainforest, while on the east side it's near desert. Yakima only gets 8 inches of precipitation a year because it's on the leeward side. So it's because of this uplift that you get so much water. So we can extrapolate, but this is only for a winter. And that 14 meters, you saw the water equivalent was only 2.17 meters. So 14 meters of a snowfall, but the snow compresses with time. And so snow depth may be only about 6 meters. And when you melt all that, you only have about 2.17 meters on the average water equivalent. But since ice is less dense, it's approximately 2.5 meters of ice a winter. Okay. I don't know why these extended down to the bottom like that. They weren't like that when I set this up. But anyway, what if you had a perpetual winter on Mount Rainier? Well, the 3 snowiest months with an average of 0.45 meters a month of water equivalent for 12 months would be 5.4 meters of water, which is about 6 meters of ice. So if it's a perpetual winter, which you would have in Antarctica and Greenland, by the way, you'd have some seasonal effects, but you'd have generally a perpetual winter. Just by using these areas, you get 6 meters a year. But the water is cool off the Cascade Mountains. So if the water was a lot warmer, it'd carry a lot more moisture. So what would that do? Well, here's some isotherms I drew for Antarctica. Because of the warm onshore flow, Antarctica is not going to get bitterly cold, but in the center it might be around 10 below centigrade. But you go off into the water and it's going to get warm quick. You have warm water up to 30 degrees centigrade off the coast. That's going to hold a lot more water vapor. And the warm sea surface temperatures are going to tend to hug the coast because as the cool air comes off of Antarctica, it cools the water with massive evaporation, and the colder water is denser and sinks, causing the warmer water from further north to be sucked south towards Antarctica, keeping the isotherms close to Antarctica. So rapid evaporation is proportional to the warmer the air than the sea surface temperature. I got that wrong. It's the colder the air. Got to fix that. The colder the air versus the sea surface temperature. And the drier the air. So if it's coming off land, it's going to be drier. And the stronger the wind. Those are the 3 main variables that cause rapid evaporation, which would occur off the coast of Greenland, off the coast of Antarctica. But today, the temperatures off Washington and Oregon are about 10 degrees centigrade. And the water vapor carrying capacity at various temperatures are these. At 10 degrees centigrade, it's only 9 grams per cubic meter. But at 20 degrees centigrade, it's about 17 grams per cubic meter the air can hold. At 30 degrees centigrade, it's 30 grams. So, due to the warmer water, which heats the air to hold more moisture, you can get a lot more precipitation in Antarctica. For instance, at 10 degrees centigrade sea surface temperatures off Washington, the most the air can hold at saturation or 100% humidity is 9 grams per cubic meter, which ends up with 6 meters a year for a perpetual winter. At 20 degrees centigrade, it would be 12 meters a year. At 30 degrees centigrade, it would end up 20 meters a year you can accumulate in a perpetual winter on Antarctica. You're starting to see how possible this is. Now, I don't know the exact storm situations, but storms would round Antarctica caused by the westerlies in the mid-latitudes. They would continually go around your main storm tracks, and then the minor storm track would cut through West Antarctica until West Antarctica glaciated. So these would continually storms go around, and the most precipitation occurs on the cold side of the storm, which would be Antarctica in this case. So Antarctica, picking up much more water vapor for a perpetual winter, could collect at the beginning 20 meters a year possibly. So yes, and here would be the accumulation with time since the flood. In about 150 years, you get up towards 2,000 meters which is compressed down to 1,500 meters with compression. And because the ocean's still warm, the ice age is going, it's going to continue to build, but at a slower rate, and finally reach a peak in that amount of time. And there's evidence of this warm water in that the Gamstsef Mountains in central East Antarctica have cirques. Formed cirques, that means the ice started at the high altitudes of the mountains first, descended down. And using a standard lapse rate, you get temperatures of over 20 degrees centigrade for the air off the coast. So there is evidence of the warmer water and air at the start of the ice age. But that's not the only one. Volcanic eruptions down deep in the ice are spread over many years. But volcanic eruptions don't last more than maybe just a part of a year, indicating that these layers accumulated faster. Also, the Gamstsef Mountains show little erosion, indicating rapid glaciation. I'm going to skip down to the fourth one. I just discovered this yesterday. Near the South Pole, send radar through the ice sheet, and it bounces off mostly ash layers from volcanism. And so you see that those are timelines. And there's one place near the South Pole where the timelines converge down 400 meters. And they melt at 6 centimeters a year based on a higher geothermal heat. And so that would give you a time scale of only about 7,000 years for that event. Anyway, there is evidence. There's two final explanations. Why do West Antarctic ice cores show only a partial ice age? And what about those other variables correlated to temperature? See, you have a lot of other variables like carbon dioxide, correlated dust, are correlated. Well, this is how I think. This is a general ice age profile for one ice age. You see this in Greenland. And in West Antarctica, the bird core only went down to this level, but the waste divide only got a half ice age. Why a half? And why does bird pick up more of the ice age? Well, I think it's because of the unique situation of mountains and oceans. For instance, ice is going to start, and snow is going to start to form with the warm water at the tops of the mountains at the very beginning, right after the flood. And then with time, maybe 100, 150 years, the glaciation is going to reach sea level. And that's where the bird core starts, maybe about 150, 200 years after the start of glaciation. And that's why it only shows maybe 80% of an ice age. But waste divide is down in the ocean. And that would take longer because you have to form ice over the ocean, has to cool off, form ice, and then it builds up from there. And that takes time, and that's why waste divide, which is over the ocean core, only shows half the ice age. Fits in pretty well. And there's all these variables that are correlated, like carbon dioxide, right in here. This is just one short little segment with oxygen isotope ratios, which is correlated to temperature. So, and here's dust in there. The reason we have those correlations is I believe in a rapid ice age is because, as I published in my 1990 book, which is out of print, volcanism is variable. It's variable between the hemispheres. Each hemisphere is is generally independent. But if the volcanism is in the tropics, it goes to both hemispheres. But whatever happened in the Antarctica, the southern hemisphere would be different. But in volcanism, you have peaks and lulls. And when you have these peaks, you have more volcanism, which causes cooler temperatures and causes all those correlations during low peaks. And then lulls, it goes back. And I believe these are on a decadal scale, not a millennial scale. So those millennial oscillations and their correlations can be explained by decadal oscillations in volcanism in each hemisphere. Result of decadal oscillations, higher volcanism causes colder land, which causes stronger winds, which causes more evaporation, which causes cooler sea surface temperatures, which causes increased ocean sodium and calcium from the land, and causes more dust and calcium. So that's how you can correlate them, by peaks and lulls in volcanism as it's decreasing. It's on a decreasing trend. Okay, we can explain the ice sheets within biblical Earth history by the warmer water. The ice age, the ice sheet doesn't start in the lowlands of Greenland until about 150 years. And so, but what about those radical millennial changes? Well, here they are. This is not the GISP 2 core. This is the GRIP core and the North GRIP core. They're all about the same. And you can see they have these huge oscillations in this oxygen isotope, which imply huge temperature variations. And you have about 25 of them in here. And by the way, this is in the time scale. This is the post-ice age ice right in here. You don't have them in that, even though they try to claim they're there. But Antarctica is a lot different. You don't have such oscillations. Here's Vostok and Epicodome C. You have maybe about 8 of these, and they imply temperature changes of only a few degrees centigrade. Well, these imply maybe 20 degrees centigrade down in Greenland. And when Greenland cools, Antarctica is known to warm. So they got a problem here. They call this the bipolar seesaw. But that need not concern us here. But here's another plot of it for 15 to 80,000, showing 20 of the cycles of the 24 or 25 cycles. You can see the changes are quick, radical, and they think they last a millennium. The average is 1,470 years, but the change to that is rapid. So that has caused a paradigm change within glaciology. And they never saw these things much before. They saw them in Die 3 and Camp Century, but it was only until the GISP 2 core showed them that they said, wow, what causes that? And since they found them there, they discovered that in the 1990s, hey, they're most data sets. They never saw them before, remember. But then they started to see them in a lot of other climate data sets. You know, is there a bandwagon effect here? Yeah, I'd say so. Also, these radical changes are used to fuel the global warming alarmism. Here's a little quote indicating that the oscillations are now ubiquitous. Again, it's messed up. Anyway, so since these first discoveries from the Greenland summit cores in the early 1900s, the record of this unexpected climatic behavior has been found in many regions, including polar ice sheets, marine sediments of the Atlantic, Pacific, and Indian Oceans, and terrestrial lakes and bogs. You find them everywhere now. And in the Journal of Geophysical Research, 1997, Hammer et al., in the preface, said, the events often begin and end rapidly. Changes equal to most of the interglacial differences commonly occur over decades, and some indications more sensitive to shifts in the pattern of atmospheric circulation occur in 1 to 3 years. That's the rest of that quote you can't see. So, as quick as 1 to 3 years, you change radically, maybe 15 or 20 degrees to a different state that lasts about 1,400 years. Then you change back again quickly. Catastrophic climate changes. Wow. But it's a mystery. One of the most enigmatic and energetically debated problems in paleoclimate research continues to involve the development of a consensus theoretical understanding of the mechanisms that underlie the millennial time scale oscillations of glacial North Atlantic climate. And it's used for the global warming scare. What they say is that you get a global warming a little bit, and then it's going to hit a threshold, and then it's just going to jump up or jump down to a hot period, to another ice age within decades. That's what they believe now. This quote from Climate Dynamics says, the demonstration that natural climate variability in the last glacial cycle shifted rapidly between remarkable extremes has dramatically revised the understanding of climate change. So, but these oscillations are in the ice age part, not the post-ice age. And they represent decadal changes in volcanism, just like the oscillations in the Dome Sea core. This is what you had during the Ice Age, these decadal changes. I published this in 1990. So here's the GISP core. You can see all the rapid oscillations are in the glacial part. Some think they're in the previous interglacial, which fuels the global warming. But the oscillations after the ice age are very slight. So you don't have that in the present climate. And because they're in the ice age, they only apply to the ice age and not to the current climate. So they don't apply to the global warming scare, by the way. So we have an explanation for the radical millennial changes. I put millennial in quotes. Now we're going to go to the fifth and last part, the explanation for the Green Sahara. It's been discovered that the Sahara Desert, late in the Ice Age and even afterwards for a while, early Holocene, was very wet. You had huge lakes, many huge lakes. You had huge rivers. You had animals that lived there, like hippos, fossils. And you found man lived there by the tens of thousands in the Sahara Desert. Well, this has really been a problem, how they explain this. So here's the Sahara Desert. It's mountainous in places, but then there's these huge sand sheets. By the way, the central mountains there are pretty high, up over 3,000 meters. And would you believe that in about 1900, they discovered live crocodiles in the mountains of the Sahara in a playa lakes? Live crocodiles, 1900, indicating that this whole climate thing was not that long ago. Of course, the Sahara Desert is mostly sand. And there's man's carved tens of thousands of figures on rocks like this. So it's well inhabited during the Ice Age and afterward for quite a while. And so the Sahara Desert is, looking at the general circulation, you have these high pressure centers at 30 degrees north and 30 degrees south called the horse latitudes. And the air sinks. That's where your major deserts and dry areas from 30 degrees north and south latitude. Now, the sinking air converges towards the equator, as you see in these trade winds here. And they end up converging and forming what's called the Intertropical Convergence Zone, ITCZ, which is a huge rain belt across the Earth near the equator in this area right in here. And that's why Central Africa is very wet and why the Sahara is very dry. In between is the Sahel, which is intermediate. But in dry areas, we had evidence of lakes during the Ice Age all over the Earth. Southwest U.S. is a typical area where we have these huge lakes. Like, for instance, here's Lake Bonneville. Current Great Salt Lake is 12 feet deep on the average right in there, but Lake Bonneville was 800 feet deep and about 12 times the area. And it overtopped a pass here and flooded down the Snake River for the Bonneville flood. There's other lakes. This is Death Valley down here. There was a lake 600 feet deep. These are called pluvial lakes. So these are associated with the Ice Age. But they lasted quite a while in the Sahara, but not in these areas. And you can see some of the shorelines from the huge lakes in the Great Basin. Like here's the series of shoreline north of Salt Lake City. So this green area is the rain belt from the Intertropical Convergence Zone. And here's the dry Sahara. Based on oxygen isotope ratios found in these areas, it's indicating that the water that fell was warm. It wasn't from the north cold climate. So it appears that this area down here shifted up into the Sahara. Now it's also called the West African monsoon, but meteorologists call it the Intertropical Convergence Zone, where the trade winds from each hemisphere converge and forcing air to uplift. And by the way, 98% of precipitation is formed by air forced up, either forced up over mountain range or forced up in a low pressure system. In this case, forced up by the convergence of the trade winds. But the ITCZ moves 12 degrees per season. It moves towards the warmer hemisphere, the summer hemisphere. It moves 12 degrees towards that. And then when it becomes winter there, it goes back 12 degrees. So it shifts 12 degrees between the seasons. And the northern hemisphere ice sheet reached a maximum in about 500 years and melted in 700 years after the flood. But the Ice Age, as I've already hinted, in Antarctica peaked in about 1,000 years and melted slowly back to the coast because of the larger ocean. So the Ice Age continued in the southern hemisphere, mainly Antarctica, for longer than the northern hemisphere. So you had a perpetual winter in the southern hemisphere. Well, you had almost a perpetual summer in the northern hemisphere. That would cause the ITC to shift. Instead of 12 degrees, it would shift maybe 20 or 25 degrees to the north, causing the Green Sahara. So in conclusion, the 110,000 annual layers in GISP-2 and the 800,000 years in Dome C are based on circular reasoning, assuming the Milankovitch mechanism is true. The rapid ice age can accumulate because of the warm ocean water in post-flood ice age. The catastrophic millennial changes are due to peaks and lows in hemispheric volcanism. The Green Sahara is explained by ice age maximum being 1,000 years after the flood on Antarctica. It's because the southern oceans would cool slower, so the ice age would last longer down there. So if you want to know more about it, you can read an older technical monograph, The Frozen Record from ICR. And you can get these 5 articles earlier. I've updated these actually, but if you want to get them online, I think they might be online by now. 5 articles dealing with all this. Anyway, that's all I have, and I'm open for questions.
Mike, as always, excellent work, extremely comprehensive. I love how you leave no stone unturned, and there's been a lot of positive feedback in the comment section, and we've had a solid mix of views as well. Creationists, atheists, old earth creationists, and so this is what we like to see. There's a lot of engagement on these important topics.
Yes.
And Mike, my brother, another thing I appreciate about your presentation is the fact that you revealed the many flaws in the conventional interpretation of ice cores, but then you also provided a stronger explanation based on the young earth creationist starting point.
Yes, that's what I try to do all the time. Try to explain these from our point of view instead of just criticize the conventional model.
Right. Rather than just attacking the evolutionary model, which you've pointed out can be fairly easy, you're actually providing a superior model, a better explanation.
Well, I believe so.
Mike, the first question I have for you, because I think this is an important issue, can you speak to briefly the importance of multiple working hypotheses as we engage these important topics?
Yeah, this was a concept developed by a conventional geologist, T.C. Chamberlain, in the late 1800s, when they didn't know a lot about glaciation, and when there's a lot of unknowns, he says it's good to have multiple hypotheses to explain it, because with time you prune these hypotheses or revise them, and if you get enough data, possibly only one will show superior. But if you get the ruling hypothesis too soon with all the unknowns, it tends to what's the word I'm looking for? It tends to shut down discussion in these other options. And so it rules until there's so many anomalies that people end up throwing it out, as Thomas Kuhn says in his book about scientific revolutions. So we have a lot of unknowns in various aspects of earth science. And that's why I like to use multiple working hypotheses, for instance, for flood models.
Right.
I advocate that because there's still a lot of unknowns out there. How do I know? Well, if you count the number of earth scientists doing research all around the world, it might be 10,000, and they got to publish or perish. So,
right.
Huge amount of research. In fact, new journals are being started all the time. I mean, I try to keep up with 50 earth science journals, but I can double that to 100. I'm finding new ones that suddenly are there, and because we got more research, more people doing research. So I'm estimating 10,000 earth scientists doing research says there's a lot of unknowns out there. So we got to, in some areas, use that principle of multiple working hypothesis until one explanation proves true. But it can't be suppressing other explanations before you arrive at that case. That's called the ruling hypothesis, and that's a bad situation in not only earth science, but all of science.
And that's one of the many enjoyable aspects, Mike, I believe, of creationist research, is the fact that there are a lot of unknowns, and it gives us a lot of work to do. There really just isn't enough time in the day. If we had every single answer to every single question, there'd be nothing to work on and research.
Oh yeah, there's still many questions out there. I find them all the time, and I work on some of them. And research is very slow. It sometimes takes me years to do one thing. So, but I've been at it for 50 years, so I got quite a collection of things I've been able to explain. But there's others I haven't been able to explain, and so.
And Mike, correct me if I'm. You currently have a book that you're working on, should be released. Correct me if I'm wrong. It's a more simplified version of answering this question with ice cores for
yes,
the layperson.
I've done the first draft, of which this talk is part of, and it's being reviewed right now, of a layman-friendly version. It can get little too technical in spots, but I'm trying to add figures and pictures to help the reader through that. And so Creation Ministries International will probably publish it in a year or two. A year or two, yes. Yeah, that's the way it is when you publish books.
Well, in the meantime, people can enjoy your latest book, Biblical Geology 101, that I have behind me. But it's such a significant issue because we're all too familiar with old earth creationists, theistic evolutionists, and atheists looking to deep core tests as evidence for an old earth. And so I think you're doing a fantastic job, Mike, addressing this issue. And so what I'll do is get some of these questions, as we have quite a few. And as always, I appreciate the audience interaction and engagement on these issues. That's why we do these live. And so, Mike, I'm not sure if you can see the questions on the screen, but I will.
You can't, but I'm still in my talk. Should I get out of share screen?
Sure. Yeah. Typically, the easiest way to do it is if you click escape on the keyboard. Yep. Looks like you.
I did it.
Okay. It's good to see you again, Mike.
Yeah, you too. I'm glad you're all up there.
Yes. that was close to a 2-hour presentation, but it flew by because it was so comprehensive and you're touching on so many interesting points. As many people in the comment section even said, as your presentation was going on, they would point out, oh, he just addressed my question. Oh, Mike just answered my question. And so you predicted a lot of questions that would come up and you addressed them directly in your talk, Mike. And so I do apologize if some of these questions you've already touched on.
Yeah, I'm surprised it was that long. I thought it'd be long, and I was tempted to not talk about the last two topics, but they were short, so couldn't help myself. So.
Mike, we don't mind. We don't mind, brother. We're used to comprehensive talks. It's what I prefer, as a matter of fact. So very good work. I appreciate it. And so, okay, here's our first question, Scriptures and Stones. I do appreciate the question here you have for Mike. So he says, in Michael's model, in brackets, he says, great name, by the way, mine too. Nice to meet you, Mike, in the chat. And he says, how soon after the flood was the Ice Age glaciation, and how did plants have time to spread out to the northern regions afterwards?
Well, that's a couple of questions. There's a segment of creation scientists that want to hold the Ice Age off for a couple hundred years because they believe the Cenozoic is post-flood. So you got a lot of events in the Cenozoic. And I've always told them that there's just way too much in the Cenozoic for it to be post-flood. And I have 33 reasons on my website why practically all the Cenozoic is from the flood. But as far as the ice age starting, you have everything, all the ingredients there ready for it to start. You have volcanism to reflect sunlight back to space. And a lot of the volcanic ash on the ground acts like snow. So you're going to get a lot of reflection from volcanic ash on the land. And you got the warm water, so it's all ready to go. But because of the warm onshore flow, it's going to be slow to develop in a lot of places because they're affected by the warm ocean, like the Western U.S. and Great Britain, and would be slow to glaciate. So glaciation would start right away in areas far from onshore flow, like in central Canada. I showed you those schematics of postulated ice age 50, 100, and 200 years. And they start in favorable areas first, and then they slowly expand from there. And of course, the high mountains are glaciated first. And then it just mushrooms from there. And so it doesn't start everywhere right after the ice, but it starts in seed areas like central Canada, northeast Europe would be seed areas that would start, and then all the high mountains over the whole Earth, including the tropics. So it started at the right and in favorable areas right away. So the second question is, how did plants have time to spread to the northern regions afterwards? Probably a lot of reasons. There was Siberia, the lowlands of Siberia and Alaska were not glaciated, so a lot of plants were there during the whole ice age. And then you had a lot of plants and trees south of the ice sheet. When the ice sheets melted, they would just expand their territory from where they occurred in the ice age. So I hope that answers that question.
Yeah, I think you did a good job, Mike. I appreciate it. Of course, scriptures and stones, if you wanted to elaborate or follow up on anything, feel free to do so, and I'll do my best to get it up on the screen. And so, okay, here's the next question, comes in from a skeptic. And I feel you addressed this near the end, Mike, but feel free to speak to it a little bit more. And so Andrew Cumming, he says, I might have missed this. Why does Mike think the ice cores with ash in them cannot be dated radiometrically?
Because it's too thin on the ice sheets. Potentially you could if you had sensitive enough instruments, but as far as I know, they don't do that. They've had other methods of dating, like beryllium-10 oscillations, but they're all correlated before you use them. So to sum it up, the ash layers are just too thin to be able to date radiometrically in the ice sheets. Now, in the sediments, it's different. You can get some nice beds that you can date radiometrically.
Thank you, Mike. So here's the next question. Winsburg Sandbox. Appreciate the question. Michael Ord. Are you aware of Dr. Steve Gallmer's post-flood climate modeling? And if so, what do you think of it?
Great question. I'm quite familiar with his model. I think his model has a lot of problems. That's the reason why I never went that route. I just went with basic meteorology ideas. One of his problems is the initial conditions. In the 2023 International Conference on Creationism, in what he didn't hardly get any ice. I think he collected only a few meters. And that totally goes against observations. And then he had the Arctic Ocean freeze up real quick, which makes me wonder about his sea ice model. But anyway, he has to get his initial conditions down. He doesn't get enough cooling over land. And once you start getting a snow cover and it gets deep enough, you get a lot of reflectivity there and it'll cause cooling. But volcanic ash spread all over from a huge amount of volcanism early in the Ice Age would act like a snow cover. And so you get a lot more cooling over the land. And he doesn't have that in his model. And one thing that model has taught me is the power of the warm water. And so, and it's possible that my initial ocean temperature, 30 degrees centigrade, might be too warm. He goes down, he started with 30 degrees centigrade and went to 24. He still has problems at 24 degrees centigrade average temperature. But I think it needs to be developed better. But he's trying to do it with, I forgot the model number, but that's not beside the point. So I wish him luck. And he might get some solid results that will cause me to have to change my Ice Age model. So that's the way science is. I might have to change some things.
Would this fall in line with the concept or idea that we were talking about earlier, Mike, of multiple working hypotheses, especially within the young Earth creationist
yes.
viewpoint? Yeah.
Yeah. I applaud his work. I hope he continues and improves it. And actually produces an Ice Age, which he failed to do in the last International Conference on Creationism in 2023.
Well, I appreciate the question from Winsberg Sandbox. This is David Winsberg. He was here about a month ago and he gave a thought-provoking presentation on the heat problem. Actually, he published 2 abstracts at the latest ICC. And so Winsberg here is doing some fantastic work as well. So I appreciate the question. And okay. Next one comes in from Young Earth Creation. Question for Mike Oard. Is it true that they can only count around 2,000 layers before the weight has compressed any below it into a single mass and they can no longer count them? How do they get dates below those?
That's roughly true. So as you pile up ice, it compresses with the lowest layers compressing the most because they have the most weight. So in their model, as the annual layers thin with depth and they get more difficult to count. And you get down there, it's hard to say how far down in the ice sheet the annual layers disappear, but I guess too, the oxygen isotope annual layer disappeared in 300 meters, which is rather odd. So yeah, the deeper you get down there, the harder they are in their time scale. And it's because they have a thinning function based on old Earth. But if we have a huge amount of accumulation, you don't get rid of the annual layers or the subannual layers. They're there. They'll count them as annual layers, but we would count them as storm or within storm layers. And you got to take that compression into account. Let me see the question again. It won't be a single mass. It'll just be they'll compress, but they'll still be there. You'll see the like for 150 years, I'd say it compressed maybe about 40%. And so, but the layers are still there that fell. You don't have a big mass. And they get those dates by their assumptions below the layers where you can't really count annual layers very well because they get too many annual layers of cloudy bands, clear bands as you get down there. And so you got to have the flow models tied to their already ice age paradigm dates and everything. According to the Milankovitch theory, that sets the time scale. And so anyway, it's kind of a roundabout way of saying it, but I hope I answered it in the process.
Yes, I appreciate it, Mike. Very good. Okay, so the next one here is more of a criticism or maybe a rebuttal. And so a comment here from Atheist Junior, and I'm wondering what the best way to respond to someone who would say ice cores can be cross-confirmed by comparing them to oceanic cores. I'm assuming he would argue to demonstrate an older Earth.
Well, yeah, because they're all of them are correlated to the Milankovitch mechanism. They originally dated deep sea cores by Milankovitch mechanism, supposedly proving it in a 1976 paper by Hayes, Shackleton, and Opdyke. That Hebert, and they changed the tie point, and Jake Hebert of ICR reran the whole thing and found out that it throws the whole thing off. So that was assumed true back in the 1976 paper. And would you believe there are thousands of papers written assuming the Milankovitch is true, not only for the Ice Age time period, but down in the sediments, in the Cenozoic, and even going deeper than the Cenozoic. Thousands of papers assume it based on that assumption. And so that's the problem. So what's the original question? Oh, yeah. The deep sea cores were dated by Milankovitch, and they just simply dated by wiggle matching. You saw those wiggles in Dome C with deuterium isotopes. They wiggled up and down. There's 8 of them, which only the top one is the top half. But then get further down, they're not. You got 7 of them in the bottom 1,500 meters. They wiggle, and they matched those wiggles to deep sea cores. That's how they dated it. It's a circular reasoning, is what it is. Sorry about that.
No, that's good, and I appreciated how you pointed that out several times in your presentation, that this is circular reasoning, and they're taking that primary assumption, that basic assumption, and writing papers based on it. So the paper is being written and the data is being interpreted based on a false assumption.
Exactly. And John Reed and I had a 4-part article in the Creation Research Society Quarterly where we delved into the Milankovitch mechanism in a lot further depth. I think starting about 7 years ago and ending about 3 years ago. You might be able to get them online now. But anyway, I've dealt with that several different times, but that's the latest I've dealt with that Milankovitch mechanism.
Very good, Mike. Okay, I appreciate it. Okay, next one comes in from Robin Webster. Thank you very much for the question. And the question is this: the deep sea record of Del 180 shows that many glaciers are millions of years in age. Can he explain why these numbers are far different than what he is proposing?
Yeah, that's oxygen isotope ratios at Del 18O for oxygen. It's because they got a whole system of dating of deep sea cores by various methods, radioactive, fossil dating. And yeah, it's all dated into millions of years. And then they go to the ice sheets and they end up dating those for millions of years. And these numbers are far different because I think those oscillations we see in deep sea cores are also related to decadal changes in volcanism, where you have rapid deposition of deep ocean organisms. This is a whole area that no creationists, I've dabbled in it, no creationists have gone into the ocean bottom sediments. I mean, there's thousands of piston cores and deep drilled cores with a huge amount of data. And yeah, they got a whole system already dated into millions of years for all that. And it's all set up. And it's based on their time scale. They've assumed the time scale, and used it to date those deep sea cores into millions of years. And those oscillations, I think, are due to rapid changes in volcanism that affect the oceans as well as the atmosphere. And so you get the deep sea core oscillations also, I believe, by decadal oscillations in volcanism.
And there's a good, solid research project for a creationist in the future: ocean bottom sediment.
Yeah. How do they relate? I can. I better not get off on that rabbit trail.
It could be a talk for a future show for sure. A lot of these points and topics that we get into can have their own 2 to 3 hour show.
I know.
Okay, well, very good. Here's the next one. Comes in from follow-up from Scriptures and Stones.
Okay.
Does Mike Oard's model account for the glacial maximum globally in its accumulation rates?
Yeah, my Ice Age model. Yeah, It about 500 years, approximately. These are rough estimates to reach glacial maximum in the northern hemisphere, and then it melts pretty fast, especially along the edge, because of a much lower albedo or reflectivity. So it can melt as soon as 70 years along the edge. About 200 years interior Canada and interior Scandinavia. So it's a 700-year ice age in the northern hemisphere and reaches a maximum about 1,000 years in the southern hemisphere, mainly Antarctica, and then slowly decreases to the present where we see today, where it's actually extended out onto the continental shelf pretty good. And then most of it's melted back to the coastal areas, and it's actually decreased a couple of 100 meters along the edges of the Antarctic ice sheet. So, see, did I answer that question? Yeah, that's part of my Ice Age model. And I'm going to have a new book out on that topic this year sometime.
Awesome. I'll be one of the first to pick it up and read it, Mike.
From Creation Industries International.
Perfect. So my own question based on your Ice Age related model, and we've talked about this in the past, but I think it's an important one to ask here in this show, is that the Ice Age related animals like the saber-toothed tigers, the mammoths, a lot of these animals that you see depicted in these Ice Age children's movies, would you say that those all came about through eco-glacial adaptive episodes essentially during this post-flood Ice Age period, Mike?
Well, when you have the model I developed, you end up with mild winters and cool summers. And that would, it's called equitable, and it'd be mild in general. So you have a lot of animals that are adapted to mild winters. And like in Siberia, there's at least 40 different mammals there, and Alaska. And so so these animals just mushroomed. Like they consider that Siberia was like the Serengeti of Africa. There were so many of them. and the number of carcasses of mammoths, and especially mammoths, you find, is millions estimated from what we've found so far. So it was a very healthy ecosystem. And so the animals mushroomed south of the ice sheet and up in Siberia, the lowlands of Siberia and Alaska that were not glaciated, which is a major mystery of glaciology. Did I answer the question?
Yes. And correct me if I'm wrong, we find a lot of megafauna in Ice Age deposits, these just really massive creatures. And so
Siberia.
Yeah.
In the permafrost. They're not in ice. They're not in glacial ice. They're in permafrost, which has a lot of ice in it. But the ice forms in the permafrost as it's forming. So, and the permafrost up there is mostly windblown silt. So that opens up a whole new avenue to explain the mammoths. And I think I've had a talk on that, I believe.
Yes. A very in-depth talk here on the channel that is listed in the description box for anybody who hasn't yet seen that. And so essentially my last question on this issue would be then, because I've seen some creationists propose that mammoths or some of these other creatures that seem to be built for eco-glacial environments are pre-flood, but you're pointing out that these are post-flood adaptations basically to the environment.
Woolly mammoth had adaptations for cold, small ears, oil glands, which they never thought they had before, but because they had poor samples, anal flap, long hair. Yeah, they had to endure some cold, generally cold climates, and so yeah, they were cold. They were pre-flood. Yeah, there's that one idea that pre-flood, and at their pre-flood, they'd be at the bottom of the sediments, but they're at the top in the permafrost.
Right.
I've gone over that mammoth talk.
You did in great detail too. So, okay, well, I appreciate that, Mike. The next question that comes in here from Doc, a skeptic, and we do appreciate our skeptics and their challenges here. And so he's asking question, and from my understanding, Doc here is a paleontologist, and so he's wondering, why do the ice sheets contain layers of ash from volcanic eruptions whose radiometric ages correspond accurately to their age according to seasonal layers?
Well, volcanic ash doesn't follow seasonal layers. It erupts maybe either in a matter of days to maybe weeks at the most. And the Ice Age part, the Greenland ice cores have a huge amount of ash layers in them, but in general, they're either too thin or they're detected by sulfuric acid spikes. That's generally how they tell them, because it's so thin that you don't find a lot of the ash itself. You find the sulfuric acid spikes, and there's supposed to be hundreds of them in the Ice Age part of the Greenland ice sheet. So yeah, there's a lot of them there, but they're just not thick enough to be dated radiometrically. Let's see, did I ask? But the reason they contain all those volcanic layers, because there was a lot of eruptions going on early in the Ice Age. Lots of evidence for Ice Age volcanism globally. And that's probably because the Earth was settling down from the flood, and that there were still areas that were not quite settled, so that they're connected to the deep a little more. There's cracks, fissures, and so there's a lot of volcanism in the Ice Age that tapered off radically after. So I hope I answered that question.
Lots of evidence for post-flood catastrophism.
Volcanism.
Yeah.
Volcanism, and that would cool the land because sunlight reflects off the small sulfuric acid particles that are trapped in the stratosphere for anywhere from 3 to 10 years, depending on how high up in the stratosphere the volcanic eruption occurred. That's what causes the cooling over the land.
Very good, Mike. Excellent answers. Centurion 737. Question. Can carbon-14 or radiometric dating be used to test these ice cores? If not, what is the reason?
I think they've tried carbon-14, but there's so little of the material, and the ash is very thin at best. They're more acid spikes, acidity spikes, that they're unable to use them. I think they tried carbon-14 once, but it fizzled really quick, and I can't remember the reason why for carbon-14. But radiometric dating, it just don't have enough of ash. Sometimes there's probably a few ash beds that are thick enough, and especially Antarctica has some that because of close by eruptions from Antarctica, but I haven't heard of them doing that. So,
would I be correct to say, given the age that they believe these ice cores are, and then the ash that would go along with them, I guess, using C14 dating, they believe carbon-14 decays too quickly, half-life's too short, so they kind of would just disregard that?
Well, that's one of the problems. But potentially it can date the younger ice with it, but it fizzled for some reason. I don't remember the reason why.
Okay, well, great question. Appreciate the thoughts, Mike. So next one comes in from Mr. Anderson. Had anyone ever done the math in how cold the Earth would have had to be in order to freeze the requisite amount of water to create the proposed glaciers in this 500-year time frame?
I'm trying to absorb the question. In order to freeze, I'd have to say the short answer is no. I certainly haven't done it. I don't really see it as a problem. Let's see. You get the evaporation from the warm ocean, condenses into storms, deposited as snow in the high and mid latitudes in the mountain ranges of the Earth. I've never seen it as a problem. So, and I haven't done any calculations. I haven't seen a need for it, but maybe the time will come where I will see a need. So I don't know. There's still a lot of research to do on the Ice Age.
That's right. Work till the second coming, that's for sure.
Yeah.
So basically, according to your model, we throw all of this water into ice caps. Would that explain a lot of the migration patterns that we see with these animals? Because then that would expose a lot of the lands. You'd have a lot of land bridges that are connecting various land masses for creatures to migrate.
Yeah, the land bridges.
Yeah.
We know there was a good land bridge connecting England with France, and that got broke sometime during the Ice Age, probably towards the end, and that's how you got all those hippopotamus fossils up into England. Yeah, during the Ice Age, there's at least 100 locations where you find hippo fossils with cold climate animals.
Interesting.
And they would have walked over there on a land bridge that got destroyed, probably from a lake in southern North Sea that broke through. So that one's pretty solid. And of course, they got stuck there, the hippos. By the way, the hippos are found in France and Germany. And the reason why is because that area by warm onshore flow would have been warm and wet early in the Ice Age, much different than today. And so it would have been a great climate for hippos to migrate into after they spread from the mountains of Ararat. But in my model, the ice sheets were thinner. Approximately 40% is thin. So sea level was only down to about minus about 55 meters.
Okay.
That would barely expose the Bering land bridge at the peak of the Ice Age, when winters were bitterly cold and there was no ice-free corridor down the east slopes of the Rockies that was made by the downslope foehn winds. But the two ice sheets, the Cordillera and the Laurentide, would have coalesced then. So I've changed my mind that based on those things, and one other piece of data, that the Bering Land Bridge was high early in the flood, tectonically. And I do not have any evidence for that. It's a deduction based on the fact that if you wait to the end of the Ice Age and sea level was low enough to expose it, it's going to be bitterly cold winter. So a lot of those animals couldn't round up there, and they couldn't get down into the southern United States through the ice-free corridor. And they have found Columbian mammoths and bisons in central British Columbia around Prince George area. It's kind of a low elevation there that are covered with glacial till. In other words, they were there before the Ice Age covered them up. So in British Columbia, the ice would have started in the mountains because of warm onshore flow. The lowlands would have stayed unglaciated for quite a while. So as the animals rounded the Bering Land Bridge early in the Ice Age, coming down the ice-free corridor, there's a gap in the Rocky Mountains called the Peace River Water Gap, where they can go right through the Rocky Mountains and into the area of Prince George and live there for a while, and then get trapped as ice spread from the mountains to the lowlands and covered them up. And that had to happen early in the Ice Age before the lowlands of central British Columbia were glaciated. So I've totally changed my mind on the Bering Land Bridge. And I don't think there was a land bridge from Southeast Australia to Southeast Asia to Australia. So I have a different scenario for those. But anyway, that's my take on the land bridges.
Well, I appreciate it.
Yeah, you only have 10 more minutes. I gotta eat and then start my Bible study.
Yes, actually, I was going to say, since we're at the 2 hour and 26-minute mark, we'll wrap it up in terms of questions there, because I do believe that we have in many ways left no stone unturned. Mike, we can schedule something again in the future, of course. And so that way, if the audience has any follow-up questions, we'll give them the opportunity to send those in, and we can engage them, Mike, because I do appreciate your time. I know how busy you are. You got a Bible study coming up. And so what a blessing for those who get to fellowship with you and learn from you, my brother. Mike, you are an encyclopedia worth of information. I really enjoyed this. This is an incredibly important topic. It is a subject matter that critics of young Earth creationists are just constantly implementing as an argument for an older Earth. So you did a great job, Mike. Again, I really appreciate your time. I want to hand it to you in case you had any final words, final thoughts.
Yeah, I have a final thought for the skeptics that are listening. I first of all, thank you for listening. The number one thing you should do, like we do, is gather all what we say first. Many skeptics, I discover that they don't really know our model very well. Like those quotes I gave from Bill Nye and Hugh Ross. You got to understand it. You got to see what our position is first, and then you can ask some really good questions, I'm sure. So please do your homework first, and I appreciate that, and I like engaging when you've done your homework. So please do that. I appreciate it. I do it for your challenges.
Amen. Yes, you do. You've got a lot of homework, and you're very diligent in that. That was one thing I wanted to point out earlier, and I completely forgot. I liked how you pointed out in these quotes from Richard Dawkins or from Bill Nye and Hugh Ross, because they are two of the more prominent skeptics of young Earth creation. And so it's important that our critics are doing their homework in order that they can address our best arguments and models, Mike.
Yes.
Okay, excellent final words, final thoughts. Again, great job, Mike. This was excellent. I want to encourage our audience to share this around, because the truth is important, and it's important that we engage these issues in a comprehensive manner. And so, Mike, God bless you. To the audience, God bless. Thank you so much for tuning in, and we'll see you again soon. Standing for Truth is out.
Okay.